Hi. In this next video, we're going to consider what happens when we take the models we've been using, but realize that the molecules really will interact with one another, meaning that they don't act like ideal gas particles. In doing that, we're going to consider a couple of models that are frequently used for things. Look at something known as a Leonard-Jones potential for interactions between pairs of molecules, and we'll also do some work with the Waals model, which is another model that you might be familiar with from doing things with working with gas laws and what have you. Before we do that, I have a question for us to think about, looking back to the last video, which involved finding the equilibrium constant for that dissociation of hydrogen. So in that calculation I did in that last video, which hopefully you've had a chance to read through, we found the equilibrium constant K for the reaction here, the dissociation of hydrogen into atoms, and we used the fact that the ground electronic state for the hydrogen atom has a degeneracy of 2. I mentioned that degeneracy is because the one electron in that hydrogen atom could be spin up or it could be spin down, right? So there's 2 states which would have the same energy, and so that was part of the partition function for the hydrogen atom we used in doing this, okay? Suppose, just for the sake of a weird thought experiment, that we took that equilibrium and we let the system come to equilibrium while it was in a magnetic field. In the magnetic field, the energies of those 2 spin states, the spin up and spin down states, would actually differ because one of them would line up with the magnetic field and one of them would oppose it, and so that degeneracy would be taken away. What would that make happen to the value of the equilibrium constant K? Take a moment if you want to think about that. Because we're doing these this way, if you want some time to think about it, you can just pause the video. So I'll just continue rather than sit here and try and guess how long it might take somebody to think about that. So if we think about the way the equation works that we used to do this, I put the equation down here, right? So this is the equation that got us the partition function. We have that product of terms in there, which is the partition functions for the products, essentially, over the partitions functions for the reactants, all raised to powers that match the stoichiometric coefficients, right? Because that's what this new I up there tells us. In our case, the hydrogen atom, the thing that has had its situation change, is the product, and so it's on top. If we change that degeneracy, if we split the degeneracy so the 2 energy levels that used to be side by side, instead of being at the same energy, they become one above the other, then that electronic partition function, instead of being equal to rough to 2, will actually be much closer to 1, right? And so if we do that, we'll actually shrink the partition function for the hydrogen atom product. That's in the numerator of the expression over there. And so that means, as strange as it might seem, if we take this equilibrium and put it in the magnetic field, our equations tell us that what should happen is that the equilibrium constant will have to decrease because we'll be shrinking a term which is in the top of the expression we used to get it, okay? At least to me, that's a very strange thing to contemplate. You have a system at equilibrium and you stick it someplace in a magnetic field, and the equilibrium moves in response to that, but that is indeed what should happen. We're probably exaggerating what would happen in reality, because when we say those 2 levels split in energy, they don't split super far, and so the partition function would really not be very likely to be changing from 2 to 1, although it should get a bit smaller if we put the one level below the other. All right, enough looking back to last time. Let's get going on the topic at hand, which is we want to start to think about the idea of having the molecules interact with one another. Okay. Everything we've looked at so far, including the fact that in the calculation we did last time for that equilibrium constant, we've said we were going to start off by thinking about non-interacting or ideal gas particles, right? Particles that do not interact at any sort of distance from one another. It's kind of a strange notion that we actually did a calculation saying that the particles were not interacting, but that they could possibly react with each other, right? Because in that hydrogen dissociation equilibrium, I say that occasionally I have 2 hydrogen atoms stick back together to make an H2 molecule. The fact that that can happen while I'm still thinking the molecules are ideal gases should strike us as kind of not right. If all the equations we had only worked for things that were non-interacting molecules, then a lot of this complicated work we've done to get to things would not be of the most use, right? So it, not surprisingly perhaps, does turn out that there are ways to take into account the fact that the particles will interact. That does make lots of things more complicated, and so in a few places here we're just going to kind of cut to results rather than do full-blown derivations of how things are going to turn out. There are a couple of models for intermolecular interactions, sorry, that you may already be familiar with. One of those is the van der Waals equation, which is on the bottom of the screen here. This one shows up occasionally in Gen Chem classes near the end of the chapter dealing with gases, where we admit that the ideal gas law is a limiting case and it's not perfect for all gases under all situations. If you don't remember that in that equation, what we've got are, the VMs in both of those equations are molar volumes, and so this is for moles of gas, right? If we look at that in the van der Waals equation, we've introduced two parameters, A and B. Those parameters would actually vary from one gas to another, right? So the beauty of the ideal gas law is in its simplicity, the fact that there are no constants or terms in it that are specific to what kind of gas we're talking about, right? In the van der Waals equation, we have to look up the values of A and B individually for whatever gas we're working with. And so it adds a layer of complexity, plus the equation itself is obviously a little bit more complicated looking than the ideal gas law. If you look at that equation, you should be able to see that if we let A and B both go to 0, then it turns into the ideal gas law, right? So in the limit that both of those constants are very small, then we get an ideal gas, right? The equation above that is something known as the virial equation, which my understanding is that it's likely that you may have worked with in one or more of your engineering classes. That one has, again, a variety of terms in it there, where it's got the B, C, and hypothetically at least so on terms up there, which are virial coefficients, which again would depend on the identity of the gas that you're talking about, all right? Equations like this are obviously more of a nuisance to work with. They're sometimes necessary when we're under conditions where the ideal gas law is likely to fail. In general, that means situations where the temperature is low or where the pressure is high. So the reason why I'm aware that in engineering classes you're likely to have encountered these equations is because a lot of engineering situations work with gases at high pressure, because if you're actually in the business of trying to run reactions and make products, you want a high pressure because that means you can make more product per unit time, essentially just push more stuff through the pipe, and that leads you to often be in conditions where the ideal gas law might break down and not give you a good result, okay? So those are a couple of equations that you might have encountered for things. A model that we often use in chemistry side of things for describing intermolecular forces is something known as the Leonard-Jones potential, also sometimes referred to as a 6-12 potential because it's got the exponents that are in there are at 6 and 12, okay? What does it say? It says the V is a potential energy, right? So this says the interaction energy between two particles has a constant term out in front here for epsilon. Then it's got R here is the distance the two molecules are apart, right? So this is the potential as a function of R. There are two parameters in here, which would again depend on what's the identity of the molecule, epsilon and sigma, the two things that are here, okay? Looking at the two terms, the first term is positive and the second term is negative, all right? That means the first term is repulsive because a positive potential energy says our two molecules, our two particles want to push each other apart, right? The second term, the negative terms, that's an attractive force that says they want to pull each other together. The fact that we have distance to the 12th power on the bottom in the repulsive term says that at short distances, that one will dominate. Okay, at long distances, longer distances, the attractive part will be significant, right? So that reflects the idea that if I have two molecules, they're going to interact with each other, they might pull each other together from afar. If we try to get them too close together, where we're literally trying to put them in the same place, then the nuclei will begin to push each other apart, and that gives rise to a sharp rise in the energy, okay? Those two parameters, the epsilon here is related to what we often refer to as the weld depth. It'll become more obvious why we call it that in a second when a graph pops up that shows us how this potential varies with distance. The sigma term over here generally has to do with the size of the molecule. Okay, is it a large or small molecule? That's the big factor in that, because that's going to set what are the points that we think of as being long range and short range. Right, and that's going to depend, of course, on how big the molecule is. If my molecule is large, then they're going to be further apart, center to center distance, when they begin to actually repel one another, for example. Okay, so where do these forces come from? These forces come from a couple of things. The repulsive forces mostly is just the overly close approach of molecules where we start to get things trying to be in the same space, okay? And so that one is relatively easy to understand, where if I think of the molecules as being like hard sphere kind of things, that's the point where they're actually bumping into each other, okay? The attractive forces are often referred to as van der Waals forces, or sometimes London dispersion forces is another term you'll see in there, and there's really a bunch of different categories of these that, that kick in. In Gen Chem, you most likely learned about all these things in a little bit of a chapter that has to do with intermolecular forces or attractions. Some of those are dipole-dipole interactions. Those are relatively strong intermolecular forces, right? If the molecules have permanent dipole moments, then that will mean they'll tend to line each other up. So I have the positive end of one molecule attract itself to the negative end of the other, and so on. There are what are referred to as dipole-induced dipole interactions, which says if I have a polar molecule with a dipole moment around an otherwise nonpolar molecule, the electron cloud around this molecule will still get distorted by the presence of the charge from the one that has a permanent dipole. Those are weaker than dipole-dipole. They're stronger than the bottom category, which is the so-called London dispersion forces. That one has to do with the fact that the electron cloud around a molecule is not really static. And so even if I have a molecule like, say, H2, which has in principle a symmetric distribution of electrons, at any given instant, my electron cloud might be distorted so that the electron density is bigger on one end of the molecule than the other. If that happens, that will start to set up induced dipoles in the nearby molecules. Those forces are weak, and that's why the boiling point, say, of things like H2 is very low. The boiling point of hydrogen is something on the order of 20 Kelvin at normal atmospheric pressure, which reflects the idea that those forces are in fact very, very weak. All three of those different categories of forces have a distance dependence that goes as 1 over distance to the 6th power. So they all can be modeled with that same piece, in a sense, that is in our London, not London, our Leonard Jones potential, sorry. So here's the figure showing us what this Leonard Jones potential looks like, okay? If I do this, I've repeated the equation up here, right? So this is just reminding us what's going on. On my y-axis, I've got labeled as U from wherever I grab this figure, but I've got the potential energy of interaction between a pair of molecules, okay? My scale here is just labeled in units of epsilon, where that epsilon is the same as this epsilon here, the quantity that's out in front, which we said that was related to the well depth, okay? This figure will make somewhat evident why that is. If I go out, the fact that this thing seems to rise above 0 there is a little bit of an anomaly in however this figure was drawn by the folks that originally made it. If I come out here, I'm at very long distances, right? So if I come out here, this curve should stay level at 0, no matter how much further I go out. So that's the situation that I always think about as my two molecules are so far apart that neither one knows the other is there, right? So there's no meaningful interaction between them. There's no energy associated with that. That persists as I bring them closer together for quite a while. Eventually, when I get somewhere around, in this case, it looks like around there, what happens is that I start to drop down in potential energy, okay? And that tells me that I get to a point where eventually I go to a minimum, okay? This point down here where the minimum comes, that's labeled as that would be essentially the ideal separation between the molecules, the point of lowest energy. It tells us down here that that distance is a function of this sigma parameter, right? I said the sigma was related to how big the molecules are. You can imagine that if the molecules are relatively bigger, then their centers are going to be further apart when they get to that minimum, when they are at the best energy. If they're smaller molecules, they're going to be able to approach more closely, right? So that's what that does. My x-axis here, the label is actually this quantity over here, right? That's R over sigma. And so my minimum comes out here at a point where, I have no idea how that happened. My minimum comes out here at a point where my R over sigma value actually turns out to be 1.1, okay? As a result of this relationship here, okay? The dashed lines here, the positive one, that's the repulsive piece. So that's only the first or positive term in that equation, this one here. The downgoing dashed line, that's the attractive term, which is this one here. Okay, that goes down to negative energies because it's the attractive piece. And you can see here that at short distances, when I get significantly smaller than this R over sigma, when it gets to be equal to 1 or so, the thing that takes over is my repulsive piece, which makes this drive up to very, very sharply rising energy. Okay, that says the molecules really don't want to be that close together. That's what the model looks like. Again, in the parameters in there, epsilon tells us how deep the well is, meaning how strong is the interaction between the molecules. If epsilon is larger, that says the force of attraction between them is greater because this well is going to get deeper. You can think of epsilon as being the amount of energy that it takes to climb out of the well, meaning if I wanted to break the molecule apart, I would have to supply an amount of energy that was at least equal to that epsilon term that's in the equation. Okay, and then the sigma term, again, is related to how large the molecule is. Think of it as being related to the molecular diameter, if we picture the molecules as being a bit like hard spheres, which we often do. I put in here just some values for the Leonard-Jones parameters for some different molecules, so we can take a look at what's actually happening to things, okay? There's just a somewhat random list of gases here. The epsilon parameters are plotted as epsilon over Boltzmann's constant, so those are in units of Kelvin, which is maybe a little bit of a strange unit for an energy, but we've done that a couple times before. The sigmas are in picometers, okay? So 10 to the minus 12 meters over there. If we look at the molecules that are in here, we can see that some of the things that I would expect, I have in my size, my sigma parameter over here. I have argon atoms up at the top, and they're close to being the smallest on my list. I have BF2 here for some reason, which is an odd and somewhat very, very small light atoms in that molecule, right, and not too many of them. O2 is also somewhat similar in size with those. I have xenon down here. The xenon sigma parameter is much significantly larger than the argon parameter. That just reflects the fact that a xenon atom is much bigger than an argon atom because it's further down the periodic table. If I get to, I've got some larger molecules here. I've got a value for benzene there, which is easily the biggest on the table that I've got, because it's not really surprising that a benzene molecule is going to be physically larger than an argon atom or a nitrogen molecule or what have you in the things that are there. Over here in my column for epsilon, that's the thing that tells me the well depth, okay? So where are the small values for that? Argon, nitrogen, BF2, which is a really strange molecule. I don't know why it's in this list of things, but those are all things that are nonpolar. They have not very many electrons. The way they can interact is relatively weak, right? They're going to have to count on these dispersion forces to do that, and so their interactions are weak. If I look at argon up here versus xenon down there, obviously both of those are single atoms, right? So the interactions in both cases are those dispersion forces or London forces. The difference between them is just that xenon obviously has a lot more electrons than argon does, and so that means the chances of the electron cloud being distorted somewhat, meaning having excess electrons on one, say, side of the atom or another, is much greater when there's a lot more electrons in there to work with, all right? And again, for benzene, that's got a relatively large value here, as does chlorine. Both of those things have relatively large electron clouds around them. I wish I knew why that was happening. I'm hardly touching anything when that happens, but it's just like being in class when I advance the slides for no particular reason, I suppose. All right, so those are some values that just give us a general idea of how these things work and the idea that they correlate with things. If we were in actual class, I had a clicker question in the slide set for around here, so I left it in there, and we can take a moment. You can pause and think about it. What does it say? It says that methane has Leonard-Jones parameters. Epsilon is 148 times Boltzmann's constant, and meaning the value in that previous table would have been 148 because those were just divided by Boltzmann's constant. The sigma value is about 382 picometers, and so the question asked you, how would the parameters for carbon tetrachloride be likely to compare for those? And you can take a moment and pause the video if you want to think about what the reasons are for that. I will again, I think, just continue and say those two molecules, if we think about them, gosh, it's probably been a while since you regularly drew Lewis structures for anything, but both of those are just carbon in the center with a tetrahedral arrangement of atoms around them, right? So in methane, the 4 positions in the tetrahedron are occupied by the hydrogen atoms. In carbon tetrachloride by the chlorine atoms. So the difference is twofold, right? One is that the chlorine atoms are going to be much bigger than the hydrogen atoms, and so the CCl4 is a much larger molecule than the methane. That means the sigma parameter for the carbon tetrachloride should be much larger. The epsilon parameter, that's the one that tells us the well depth, remember, right? And so that one says that the carbon tetrachloride molecules should interact with one another more strongly because they have significantly more electrons in their general electron cloud, similar to the situation that was in that previous table for, I think it was xenon versus argon. Right, so the forces between carbon tetrachloride molecules should be stronger as well. That means epsilon and sigma should both be larger for the carbon tetrachloride, which means I guess that I'm picking D down there if we're doing this, okay. All right, we can do that in that case, by the way, largely because I made sure I picked two molecules whose structures were very similar. Right? If I had picked things that had different shapes to them as well, then it would be much more complicated to try to predict what was going to happen. We'd have to know a lot more things than we necessarily would just by popping it up and saying, I can figure this out on the fly as we go. All right. If we put these intermolecular reactions into the statistical mechanics machinery we've been working with, then we can't calculate the partition function or the energy or any of those things by going one molecule at a time. Right? All the work we did in chapter 5 up to this point, we always did by saying that, well, we were going to say if we knew all the states that one molecule could have, then we could use the states from one molecule and figure out how a large collection of molecules would be spread out over the same states, as long as no one molecule was influencing any of the others. If the particles interact, it doesn't make sense to do that, okay? To do that, there is a need to incorporate something that is known as a configuration integral, which is the phrase used over here. What that does is it's got a potential energy in it that depends on the relative positions of all the particles, meaning the distances between them, okay? That configuration integral is represented here by Z, all right? And it kind of spirals out of control relatively rapidly, right? Because this one says, all these distances over here, those are going to be the pairwise separations of pairs of particles in my collection. And if I have a collection of n particles where n is quite large, then I have a collection of a very large number of variables that is in there, okay? And that thing gives me some problems in evaluating stuff. That configuration integral Z then gets plopped in down here to modify the partition function that we had before. So the part in front of the Z in the bottom equation we've worked with before, that essentially says we calculate the partition function as if the molecules are non-interacting. That Z term out there is one that comes along and is the fix to take into account the fact that now we want to acknowledge that the particles really can exert influence on one another. And so the, say, positions, among other things, of them are not all independent from each other, okay? As you might imagine, evaluating this thing can be rather difficult, depending on what sort of models we put in for the potentials. In some cases, these integrals can actually be evaluated analytically. In other cases, they can be approximated by various numerical methods, which actually are very, very good nowadays because computers can just chug through stuff at such a high rate that it is possible to work with those things, but it's certainly not something that we're just going to splash one of those up there and ask you to evaluate. The model for gases that often is used, at least by chemists and sometimes by engineers, is for real gases is often the van der Waals model. Okay, and I mentioned that at the beginning. The van der Waals model is based on saying, well, if we have hard sphere molecules and very weak intermolecular attractions, we can put together a relatively simple potential and use that to derive an equation of state. Equation of state is a fancy name for, well, the gas law is an equation of state, right? So the ideal gas law is the equation of state for a collection of non-interacting particles. The van der Waals equation, which is on the bottom of the screen down here, that's the equation of state for a collection of particles that interact in accordance with the potential arrangement that's drawn over here. Okay, so what does this thing say? We've got a somewhat weird looking potential here, right? Instead of having the curve, it's approximated by something more or less just like a tray there that says, I've got a shallow attractive well, where the well just represents the idea that this is below, this is the zero of energy, right? So that's where the two molecules are not interacting. The depth of that attractive well, that thing is going to determine, or be determined by, if you want to think about it, that is what sets the A parameter here, okay? So that A parameter has to do with the strength of the forces between the molecules. If the molecules have strong intermolecular forces, A is going to get bigger, meaning this well over here would get deeper. Right, so that's kind of in the role, or playing the same sort of role as epsilon in the Leonard-Jones potential model. The B in the first term here, the B comes from what is referred to here as hard sphere repulsion. So that says, if I'm thinking of the molecules as hard spheres, where this vertical line kicks in, that's the point where the two molecules actually physically bump into each other, right? So that's where the center to center distance for the molecules is equal to a molecular diameter, if I'm talking about a collection of just one type of molecules. So they all are the same size. If the distance from center of one to the center of the other is a diameter, then the outside edges are bumping together. That's the point at which the potential energy goes up, because there's no way that we can force them closer together. If they're really hard spheres, that's like trying to take two bowling balls and push them together and get them to overlap. You basically can't do that. Okay, so that's the model that leads to this van der Waals equation, which when we teach this in Gen Chem, we usually just say, yeah, the ideal gas model, but there's some other equations that do real gases, and we toss up this one here and talk about it a little bit and look at how the parameters vary from different molecules. I apologize for the way the slides are jumping all around today doing this. I totally do not know why that is, but I will try to see if I can't figure out. Someday, I hope if I do this for the rest of the semester, I'll be actually getting better at it. So that van der Waals partition function, then, we can evaluate that. And here what we've done is the top version just says, well, this is the generic equation, right, that has in it this z term, where z is the configuration integral. This bottom version says it actually has replaced that configuration integral with this stuff here, which it is possible to show, but is beyond what we're going to actually try and drag ourselves through, that piece over there is what we get if we do that, that pairwise configuration integral for the different molecules, okay? So in that last term, the A and B that appear there are the van der Waals constants for the specific gas we're talking about, all right? And so the B parameter, again, is due to molecular size. You can kind of remember that because it's the one that shows up here in the term that is subtracted from the volume, right? And so if the molecules are bigger, what that's saying is that more of the volume is occupied by the actual size of the molecules. All the volume that's occupied by the actual molecules is space that the other molecules can't move into, right? So that's why it's V minus NB, because that's diminishing the available volume in which other molecules can move. The A parameter, which is up here, that one, what that again has to do with the strength of the attractive forces. So that accounts for the fact that in real molecules, when molecules collide, instead of being like hard spheres or bowling balls that just bounce off and don't do anything except transfer momentum, collisions between real molecules are usually, gosh, we often use the word sticky to say molecules come together and they actually don't immediately separate. They interact for some finite time, okay? Finite time in this case can be very short. It might be on the order of femtoseconds, say 10 to the minus 15th or so seconds, but it's still some amount of time in which they're actually clinging together, right? We know those forces exist because if those forces didn't exist, then there wouldn't be any liquids or solids, right? Everything would be a gas no matter what the temperature, and so there have to be intermolecular forces to account for that, all right? So if I take this partition function and I take some of the stuff we've done before, what I'm going to do next is try to convince us that if that's the partition function, then I can derive from there the van der Waals equation for the pressure. Okay, essentially the van der Waals equation of state for a van der Waals gas is another way to refer to that. All right, so let's get together the pieces we need to do that. Here I've got equations on the top. This is a couple of things we've talked about before, okay? So the top one here, the A, that's the Helmholtz free energy, right? That was in a flurry of equations that we kind of chugged our way through before spring break, shortly before you took the second exam. And after we got to that one, we said that the pressure is easily related to that Helmholtz free energy because the pressure is just the volume derivative of the Helmholtz energy, okay? So that, if we do a couple things, we had this equation earlier as well, which says that I've got a KT term out here, I've got 1 over Q, and I've got the derivative of Q with respect to volume, are the things I need to get from this Helmholtz energy, to get from there to having an equation for the pressure. All right. For the van der Waals equation, my previous slide asserted that this thing here is the partition function for the van der Waals gas, all right? Where again, it's got this piece out here on the end that comes from that configuration integral, all right? So what I did is, what I'm gonna do in working with this is I'm gonna take this function and I'm gonna rewrite it to call everything in front of that thing I just drew the bracket around. I'm just gonna call all that stuff alpha, okay? So alpha is the partition function without the configuration integral. In terms of what we're doing right now, alpha is the part of Q that is not a function of V, right? Why does that matter? Because up here, I'm gonna take the derivative of Q with respect to V. So when I do that, all this other stuff here is gonna get eliminated. Right? It's going to just be a constant. It's not going to be part of doing the derivative, okay? So I want to get that out of the way by just saying, for purposes of differentiating with respect to V, that all can just be written as a single term alpha, and then we can introduce later back the stuff that's there, most of which will just easily cancel when we get to that point, it turns out, okay? So that's what the alpha is that appears in the next thing. It's just this term here, okay? So armed with that, I'm going to go ahead and we're going to do a little bit of work to establish that we get the van der Waals equation out of this thing, okay? So first thing we have to do is I'm going to need that derivative, the derivative of Q with respect to volume, okay? So I've got what Q is up here. This is my Q, and I want to write down what is the derivative of Q with respect to volume, okay? And let me see if I can get this straight off of my, my notes here, all right? So when I do that, I'm gonna have my alpha in front, okay? Because that's gonna hang around, because that's the part that's not a function of V. Then from that, I'm going to get a piece that is N times V minus NB, and that comes from the piece in front. So now instead of the n power, it's going to be the n minus 1 power. Okay. That's the derivative of the first term there. So I got to multiply that by the second term. E to the n squared A over K T V, where my K there is the Boltzmann's constant. I did not put the B on it this time, it looks like. Then I'm going to have the part from the second term. That one is going to be plus V minus NB to the N. So that's the first term. And then that's got to get multiplied by the derivative of the second term, which is the exponential that's already there. It's that piece times times the derivative of the exponent, which should be I shouldn't use a different K. Come on, you can do it. Times KT V squared, and then I get to close the bracket on that part, okay? So that's all the pieces of my derivative. What I'm gonna do now is I'm gonna take that derivative and I'm gonna load that into this equation up here for P, all right? Which says I want KT over Q times this derivative, and that's supposed to get me the pressure. all right? To save a little bit of scribbling and stuff like that, I gave myself a version here, which will be able to take and just cancel things that we want to cancel in, I believe, to get to a simple result. So first of all, this alpha and that alpha will go away, right? The alpha on the top here, this one is from the derivative. This part on the bottom, that's q. Right, so if I flip back for a second, this says q is equal to that, and in here I had 1 over q, right? So this part says that was kt over q, and I also pulled the alpha that was in front of the derivative in there, so those two are going to cancel, all right? When I come to the terms in here, next up, I've got to look and see that I've got the exponential piece, the e to the n squared a over kt v, that's in all the terms that I have, right? It's in the bottom down here, so I'm going to take that one and cancel it with the 2 of these, because that's distributed over both of those terms. So those are both going to go away when I do that. All right, that gives me, for the first term, I've got, let's say, n kt on the top, because that's the n that comes from in here, together with the kt from over there, okay? Then I've got, what have I got? I've got v minus nb to the n minus 1 power here, and I've got v minus nb to the n power down there, right? So that's going to give me, on the bottom, a single v minus nb, right? Because I can cancel n minus 1 of those, and that leaves me just that piece on the bottom. Next, we need to do the second term, okay? In the second term, I have v minus nb to the n here, and I have this v minus nb to the n that's distributed across both pieces. So that's going to get taken out completely, okay? That leaves me with kt from here times this minus n squared a over kt v squared, which means the kt's cancel, and that gives me minus n squared a over v squared, okay? What that is the van der Waals equation. If we wanted to take this and make it into molar quantities, we could write a version that we see often, which is P, I could say P molar or something like that, equals RT over V molar minus B minus A over V M squared, okay? Where that just says I've gone to having 1 mole of gas. As you can see, that's the end of this video, because I just bumped the slide that was in there to remind me to stop here, okay? All right, that shows us that we can in fact get from statistical mechanics to the results that you've seen before in other cases. It's a route that actually in the development of things like this van der Waals model is a path to get to the equations that we sometimes learn elsewhere, all right? Okay, that's all for this one. Next one up is going to be pretty short. It's just going to be one last look at entropy to finish out chapter 5. Thanks.